Hi, everyone. I'm Tarisa, like Casey just said. I'm an Earth Science Master's student attending North Carolina Central University. This summer, I conducted research at the Flatiron Institute in New York as a part of the Simons National Society of Black Physicist Scholars Program and was advised by Dr. Bose from Arizona State University. So the summer research I conducted is basically on an element that is essential to all life on Earth, or all known life on Earth, phosphorus. So in this talk, I'm going to give you guys a brief overview of phosphorus, its importance, and how it was delivered to Earth. So where does phosphorus come from? Phosphorus, like a lot of elements that we come in contact with in our daily lives, comes from the center of stars. Phosphorus, more specifically, comes from the center of oxygen-rich stars through a process called nucleosynthesis. Basically, the creation of new atoms. As the star ages, it'll eventually reach a stage in its life cycle where it goes supernova or it dies. It basically means it's dead now. These oxygen-rich stars, when they reach the end of their life processes, they explode and eject freshly formed molecules such as phosphorus and other molecules in the cooler winds. These winds form multiple generations of stars these winds from multiple generations of stars enrich the interstellar medium with various elements where phosphorus-bearing organic molecules can form. When molecular clouds collapse into the solar systems, just like ours, these organic materials can be accreted by asteroids and protoplanets. So there are two ways that scientists theorized phosphorus came to Earth. So the first way is just through planetary formation. So protoplanets and protomoons were constantly crashing into each other during this period of our solar system's history. About the first 10 million years this was happening. So occasionally small asteroids or planetesimals collided and stuck with each other to form large protoplanets or planetary embryos. If asteroids were phosphorus rich, then they would bring essential phosphorus to the growing planet. The second way phosphorus could have come to Earth is through impact asteroids, as seen in that far one, after moon forming events. This is often called the delivery of volatiles, the late delivery of volatiles, and scientists argue that hydrous impactors brought water and organic Earth into organic Earth after it was fully formed. This would be the second way that phosphorus-rich materials came to Earth. Now that we know where phosphorus is synthesized and how Earth may have received this element, why should we care? Why do we care? There's a lot of reasons why we should care. Phosphorus is really important to life. Earth has its own catch of phosphorus. 98% of our phosphorus is actually in the core of the Earth. It's inaccessible. So where do we get it? So basically, the phosphorus that we come in contact with our daily life is given to us by cosmic dust that rains down every day, every year of our lives. That's where we get our phosphorus from, and we also get it from impacts from meteorites. Phosphorus is a really important component in plant life. If they didn't have it, they wouldn't be able to reproduce. They couldn't photosynthesize, and cell walls would not be able to be maintained. As far as humans, phosphorus is literally holding our DNA together. If we didn't have it, we wouldn't be here. And it also gives us energy through phospholipids. So we know how delivery was given us back in the day, but what about modern day delivery? So these days, when an asteroid lands and survives the trip through the atmosphere, it's referred to as a meteorite. Meteorites are portions of asteroids that broke off from their parent body from the main belt or the Kuiper belt seen from, the asteroid belt, Kuiper belt. It's right there. And, they make their way to Earth. In the middle panel, you can see that there's a picture of a meteorite collected from Antarctica for the ANSMET program. The surface of Antarctica, as you can see, is white. The meteorite is not. So it's very easy to be found, but meteorites can be found all over the planet. It's just very easy because white versus everything else. It's very easy to find. Sometimes meteorites can break apart into smaller particles, less than 500 microns in size. Just to give you guys a sense of scale, that's 5 times smaller than like a maybe like a grain of hair. Like it's smaller than a piece of hair, 5 times smaller than a piece of hair. So you're not going to be able to see it with the naked eye. So as you can see on the far right, that's a picture of a cosmic dust particle about one. Yeah, that's a picture of a cosmic dust particle. Can't see it with the naked eye, got to zoom in on it. Both meteorites and cosmic dust should contain phosphorus, and my research involved how much phosphorus and in what form. Are they present as organic matter? Are they present as minerals? But why focus on cosmic dust instead of meteorites? I mean, obviously one's more known than the other, right? So Earth is big, and it has a significant gravitational influence, especially when it comes to things that are very small. Because of this, Earth accretes about 40,000 metric tons of cosmic dust a year. That's like 14,000 fire trucks hitting Earth every year. I did the math, guys. I promise I'm right. We can study phosphorus' presence in meteorites or cosmic dust. Cosmic dust samples a variety of asteroids and comet sources with plenty of chemical diversity, while just meteorites come from a small number of sources. So cosmic dust has they sample from a lot of different bodies. Meteorites just only come from a few. Earth accretes a lot of cosmic dust, and that's what this plot is showing. So you can see that hump is between 200 and 300 microns in size, and that's the largest portion that Earth accretes yearly. So this is just like the main amount that Earth likes to bring in. Like it brings in other meteorites, cosmic dust particles in other sizes, but that's just the size that it likes the most, apparently. And that's where we're looking for phosphorus. It's likely to be present as organic compounds, as coating on silicate grains or phosphorus-bearing minerals. Meteorites are kind of left out because they don't come as much as 14,000 fire trucks. The Earth collects it in a much smaller amount. But how do you analyze something that's just so small? To understand the chemical composition of cosmic dust and the phosphorus contents, one has to use a laboratory tool called the Electron Microprobe. So basically it works by shooting a high energy electron beam at the particle or the molecule that's trying to be collected. It excites it, moves it to the higher state, and then when it moves back to the ground state, the atom gives off an emission, and then emission is collected, recorded. Now we know what kind of element it is. And we were using X-rays for this experiment. So this past summer, my job was to basically read literature on cosmic dust, their compositions, and their possible origins. Also looking for any information about the detection of phosphorus in cosmic dust, which wasn't there. Weird. I did, however, manage to find evidence of phosphorus-bearing molecules in molecular clouds, meaning that I was looking for phosphorus alone. I found phosphorus together with other things. So like phosphorus oxide, phosphorus nitrate, but no phosphorus by itself. We also managed to collect information about phosphorus in one cosmic dust particle. So what are the next steps of this research project? So this topic is going to become a master's thesis for North Carolina Central University. So data has been compiled and is going to continue to be compiled by me and other members of the team as the year progresses. So alongside me looking for, more evidence of phosphorus in different forms, I will also be analyzing data collected by the Electron Microprobe to better understand the composition of our planet and whatnot. And we hope to use this information to calculate the amount of phosphorus delivered to Earth currently by way of cosmic dust accretion, and then back during proto-Earth by way of synthesis through impacts. So, to summarize, phosphorus originated in oxygen-rich stars and are spread through the galaxy during a star's death. Most of Earth's phosphorus is found in the core, so the surface of the planet receives its share from asteroid belt bombardment and cosmic grain dust. Maybe that's what we're saying. Scientists argue that a good portion was likely delivered to Earth after Earth was fully formed. This number is important to know and calculate because it holds importance to plant life, human DNA, and just being alive on Earth. It's very important. So, acknowledgements. I'd like to thank Foundation, Science Foundation, Now Society of Black Physicists for hosting this program and for funding it. Thank you so much. God, thank you. I've learned so much and I'm grateful I was chosen for this opportunity. I'd like to thank my advisor, Maitri Bose, for guiding me on this project and continuing to help me through the next school year. And I'm really excited to keep working with her on this project. We have so much more to learn. I also like to thank Casey. We know how hard it was for you to be here, especially, organizing things remotely. You see the effort. You love it. Thank you. Thank you so much. All right.
Questions for Tarisa?
Does it get down to the surface typically, or is it burned up in the atmosphere and get into kind of the Earth system that way?
I mean, both, because they can be found on the surface of Antarctica. I read a paper where they found it on the roofs of houses in like urban areas as well. But it all just depends, once again, on like how it's being brought in, because even everything that goes in the atmosphere eventually has to come down at some point.
Right.
So it does make it to the Earth's surface. Is how long is, we don't know that yet.
Similar question, and that is there some space-based measurements to see if there's some filter, some bias of the data?
Could you use your seat mic, please?
Oh, thank you. Microphone check. But the question is there a space-based measurement, like using aerogel or something to get samples of cosmic dust? That's a control against what comes to the ground.
Yes, I think. And I think that's just using, I don't have like a definite answer, but it does sound like something that would happen since, you can look into molecular clouds from Earth and analyze the composition. That's not exactly what we're doing. We're focusing on stuff that makes it to Earth and analyzing stuff on Earth, but that's something I could look into though.
Cool.
There have been measurements like this for nobles, but maybe not for phosphorus.
I see.
All right. Yeah.
Experiments, X-ray experiments have to be done at special facilities?
I don't think so. I'm not 100% sure about that. I know there's only a few that are specialized in it. Arizona State University is one of those places that specialize in cosmic dust, micrometeorites, and asteroids and meteorites. So I don't know if there's a specific facility, but there are specific universities that their main focus is on stuff like this. So
thank you.
Oh, yeah, okay. How much of a role do weather patterns play in figuring out where to test for the presence of phosphorus?
That is a great question. We're looking at Antarctica. So yeah, they're just, I mean, cosmic dust is literally everywhere. We get 14,000 like fire trucks amount. We get 14,000 fire trucks every year worth of cosmic dust. So, it comes it's everywhere on the planet. It's just harder to see because, landscape, just Earth processes were prevented from being seen. But when you're at Antarctica, there's nothing there but whiteness. So very easy just to scoop it up and just go home instead of like digging through the dirt for something,